research articles. His research is also focused on ferromagnetic resonance, ultra-fast demagnetization, high-spin orbit coupling materials, Hausler alloy, etc. During his PhD, he was awarded several scholarship, travel grants, and some of them are like ILL travel grant, IEEE magnetic summer school travel grant, etc. He will join as postdoc with Matthias Ploy at this university, Gothenburg University, Germany. So over to you, Rahul. You can start.
Can you hear me?
Yes, we can hear you.
Okay, let me share my screen. So are you able to see my screen and voice also?
Yes,
Hello, can you hear me?
yes, we can see your screen.
Okay. Thank you so much, Dr. Neeru, for introduction. And I would like to congratulate Professor Mudli, who was also my supervisor during my master's at IIT Delhi. And I would like to congratulate him for completing his 10 years research at IIT Delhi. So today's talk, I will talk about Spintronic Terahertz emitter. So my outline would be like this. First, I will introduce what is the Spintronic Terahertz emitter and why it is so important, and what are the material choice for Spintronic Terahertz emitter, and then I will describe two phenomena which is utilized to emit terahertz radiation using Spintronic Terahertz emitter. So what is Spintronic Terahertz emitter? Spintronic Terahertz emitter is a spin-based device which can emit electromagnetic radiation in terahertz frequency region. So, and why the spintronics, spin-based electronics is important because, as you all know, it does not contain any Joule heating. It implies spin degree of freedom, so it can fabricate easily, and also has low cost. So, if you see this diagram, it has several applications like GMR, racetrack memories, and also in terms of transistor. So, today I will talk about the terahertz emitter, which is like the spin degree of freedom. So what is the Terahertz radiation? Terahertz radiation is the electromagnetic radiation which lies from zero point 0.1 terahertz to 30 terahertz frequency, which is also called terahertz gap. Okay? And if you see this graph, which is a global market investment dollar as a function of years. So during the last decade, you can clearly see the terahertz radiation sources and devices has global a huge investment in terms of imaging, spectroscopy, and communication. It has also several applications like in imaging, quality control, and also during in the operation. So I will give you one or two examples why terahertz radiation sources are important. So if you see this image, where you can see a man is standing, and if you incident a visible light, you cannot see any weapon which is hidden inside the pocket. But if you incident a terahertz radiation, means the terahertz radiation has a property which can so radiation cannot transmit through the metals. So by incidenting this radiation, one can clearly see this kind of hidden weapons in the body. So this is one example. Another example is so in this, as you can see this image, this is a brain of mice in different snapshots. So if you do a magnetic resonance imaging, you cannot see any kind of tumor which is inside the brain of mice. When we incident a white light, you can see some kind of damaged things here, but we don't know at which point the tumor is. And there is one more technique called optical coherence tomography, which has an advantage to see different type of tissues. You can clearly see this image is much better than these two images, but still you cannot identify where is the tumor region. So if you incident a terahertz radiation on this kind of brain, you can see this red spots, which is the tumor spots, and one can clearly see a tumor region throughout the brain image. So that has an advantage in terms of medical imaging. Also, not only in applied science, it has application in fundamental science because the it there are several fundamental modes that are available during this region. So as you all know, this is a Landau-Legit-Gilbert equation. So first two term on the right hand side represents the precessional and the damping term respectively. But if you there is also one more term which is called inertial term, and that represents by the second derivative of magnetization dynamics with respect to time, and that terms actually lies in Terahertz frequency region. So let's say if you don't have this term, if you have only Landau-Gilbert equation, you will have a precession something like this, and that corresponding to a ferromagnetic resonance mode, which lies in gigahertz range. But if you have this term, you will have something like this kind of precision, zigzag precision during the precision along the applied magnetic field, and that zigzag precision corresponding to the nutation, which is also called inertia, and that lies in Terahertz frequency. So in order to characterize these kind of properties, one would require a tunable Terahertz source, and also for applied science, one required a continuous broadband Terahertz source. So what are the Terahertz sources available in the market? So there are some different type of Terahertz sources which is based on air plasma, semiconductor based, nonlinear crystal, and spin based radius source. So if you see this graph, which is it has electric field amplitude as a function of time. So one can see that the spintronics Terahertz the amplitude of electric field for spintronics Terahertz emitter is much larger than the other conventional Terahertz emitter. But if we take the fast Fourier transform of this time domain signal, one would get a frequency and frequency domain spectra, which is you can see this red curve don't have any kind of absorption during in the range of zero point 0.1 to 12 terahertz. But other sources like zinc telluride, which has a absorption gap here, also photoconductive antenna don't have any, it is only limited to 6 terahertz. So in terms of broadband, Spintronic terahertz emitter has an advantage. So I will describe what is Spintronics, what is the physics behind the Spintronics terahertz emitter, and one physics is based on the inverse spin Hall effect. So as I said, it contains one ferromagnetic layer, also called spin source layer, together with the spin sink layer. When the incident Gaussian femtosecond laser pulse, it will create a spin magnetization pinching, and that hot electrons in the layer that will super diffuse into the non-magnetic layer, and because of the spin orbit coupling of non-magnetic field, it will convert into the charge current, and that charge current will be kind of a oscillating charge current because we have an incident oscillating pulse, and because of this accelerating and decelerating charge particle, one would get a radius of a hertz region, and this electric field amplitude can be governed by Ohm law, which is a product of effective impedance and the charge current in the metallic layer. And this charge current one can write in terms of spin Hall conductivity like gamma and the generation
Rahul, your voice
characteristic.
is little low. Uh,
Uh, can you hear me now better?
yes, it's improved.
Okay, okay. So, uh, the electric field of terahertz electric field can be governed by the Ohm's law, which is a product of effective impedance and the charge current, which is written like this. And this charge current is a function of spin, spin Hall conductivity as well as the uh, spin current generation. So, so, so let's focus on, in order to get the high amplitude of terahertz electric field, one would need to think about in terms of these parameters. So let's say if we talk about the spin Hall conductivity, so if we talk about spin Hall conductivity in this cobalt iron boron and different non-magnetic layer structure, So if we see this paper where they measured the terahertz amplitude as a function of different spin orbit coupling material, they saw that they found the highest terahertz amplitude when they had high spin orbit coupling real life platform, and which is also proportional to the spin Hall conductivity. By keeping platinum as a non-magnetic layer, they also vary the different ferromagnetic layer, and what they see that the ferromagnetic layer does not have that much impact on the terahertz emission. So from this slide, one can think about in order to get the highest amplitude or large amplitude, can uh, think about spin Hall conductivity. However, all these materials are not 100% spin polarized, since JS is also a factor in the expression. So to begin with, we thought about to manipulate the JS in ferromagnetic layer. And then we use platinum as a zinc layer. And what we thought about, since Heath-Lark compounds are known to have 100% spin polarization according to theory, and what is the spin? What is Heath-Lark compounds? It has a contains three atoms like X to Y Z type structure, which is you can see here. If X, Y, and Z atoms are placed at a proper position, it is called perfectly ordered. And the Y and Z atom are intermixed, that is called partially ordered, which is represented by P2. And if all these atoms are randomly mixed, that is called perfectly disordered structure, which is represented by A2. So this is a good material in order to get highest spin consumption. And so we have calculated, our collaborator have calculated the spin density at Fermi level, where what we have found is as we increase the ordering of this compound, we see a minimum minimum spin down density at the Fermi level when it is L to 1. So, so according to theory, we have to achieve at least L to 1 order in order to get the maximum spin concentration. So we have fabricated this sample on different substrate. So the substrate we choose silicon, MgO, and different uh, trans substrate which is transparent to the terahertz emission. But the epitaxial quality was found when CFP goes on MgO because of the lattice mismatch around 4%. Then we have measured X-ray diffraction in order to confirm the quality of our CFA structure and in the perpendicular diffraction vector geometry. And what we found is CFA 111 and 002 peak, which corresponding to the L1 and V2 mixed phase. And how do we know that? Since if we see the structure factor calculation for X-ray diffraction, one would see if it is perfectly, if the atoms are perfectly placed at the proper position, we will get this ordering and also this and if we have Y and Z atoms are intermixed, then you will this factor will cancel to this factor, and then you get only the type of structure. So from this XRD measurement, what we have found is we have a mixed phase of B2 and N21. This we have also further confirmed with the cross-sectional transmission from microscope, where you see this is the MgO region and this is the CFP, where we saw that at region 3 we saw that a square lattice, and also at region 2 we also saw a square lattice, but in the same material at position 1 we saw that hexagonal lattice. And how why this hexagonal lattice appears? So if we see, since we have measured the X-ray diffraction in perpendicular diffraction geometry, so we choose a transmission spectrum microscope zone axis along 100 MgO axis. And what we have found that CFA002 plane has this kind of square lattice on MgO002 plane. But when we do the same thing at point 1, we saw that a hexagonal kind of. So from this measurement and modeling, we confirm that our CFA has mixed field. Then further, since we know that the density of state is also proportional to the K, so we we saw that we also measured the damping parameter for our sample using ferromagnetic resonance spectroscopy by measuring the line width as a function of frequency. And what we have found that the damping is also in the order of 10 to the minus 3, which is approximately equal to the B2 or mixed phase of the CFA. Then we utilize this whole structure for Terahertz emission measurement and using time domain Terahertz spectroscopy setup. So this is a schematic of our setup where we use a titanium sphere laser to generate the femtosecond laser pulse, and that will go through the delay line, and that will incident on the emitter. So before putting our Spintronic emitter, we calibrated the whole setup using conventional emitters like LT gas, and then we replaced the LT gas emitter with our Spintronic emitter. We applied some magnetic field in order to saturate all the spins in one direction, and because of this inverse spin Hall effect and then this incident, it will generate a terahertz radiation, which will be focused on the LT gas detector. So this is a time domain signal of terahertz electric field amplitude, where if we of different thickness of platinum, and one would see if you change the magnetic field from positive direction to the negative direction, the terahertz electric field, the sign of the terahertz electric field also changes, which confirms that our signal is coming from the inverse spin Hall effect phenomena. And we also optimize the platinum thickness in order to get the maximum signal, and that thickness is corresponding to 4.5 nanometer, which is and the signal of this emitter is approximately equal to the difference iron platinum. And this is the fast Fourier transform of the time domain signal, which gives the how much is the bandwidth of our emitter, and which is approximately equal to 0.1 to 3 terahertz. Then we further optimize the signal as a function of different platinum and CFA thickness, and we utilize this thickness dependent Hertz model using the diffusion point model. And from the fitting, we can extract this parameter, which is called attenuation, Terahertz attenuation coefficient, which was found around 20 nanometer, which means after 20 nanometer thickness, whatever the terahertz is generated inside the CFA platinum layer, it will not transmit through the material itself. So here are some research highlights. So if you want to learn more about this emitter, you can follow this YouTube link. So this first, second, so far we have discussed about the spin Hall conductivity and the generation of spin current, but there is a factor called impedance, which also depends on the conductivity of the spintronic layer. So in order to see this in order to understand this phenomena, we fabricated two series of sample, which is iron platinum on MgO and iron platinum on magnesium. Why we choose MgO and magnesium aluminum oxide? Because when iron grows on MgO, it has a 4% lattice mismatch. However, when iron grows on MgO, it has 0.4% lattice, which means it is expected to have epitaxial quality of iron on both substrates, but with different macroscopic properties. So we measured rocking curve in X-ray diffraction, and what we have found that when iron grows on MgO, so when zero, iron grows on MgO, the full width half maxima along 002 plane of iron is much lesser than the when iron grows on MgO. However, when the quality of platinum is more or less similar. This we have also confirmed with temperature dependent conductivity measurement, where at room temperature we have a electron scattering plus electron deflect scattering. When we go to low temperature, we have only electron deflect scattering, which means when iron platinum grows on MgO, because of the lower conductivity, we can conclude that it has a higher deflect scattering centers because of the one order larger refractive index. Then this we have also confirmed by measuring the electrical conductivity in terahertz frequency region, which was more or less similar to what we observe in the temperature dependent DC conductivity. Then we measured the terahertz emission, and surprisingly, we found a opposite result. So when we have a larger defect scattering in the iron layers, we get larger terahertz amplitude, and this also follows this Ohm's law behavior. However, if we do the fast Fourier transform of this time domain signal in order to get the bandwidth, we get a bandwidth of 3 terahertz for iron platinum when it goes on MgO, but it is little bit higher when it goes on ME. And this is because when the terahertz signal is transmitted through the MgO or MeO substrate, MgO substrate has a phonon absorption around 3 terahertz, which you can clearly see here by in the transmission versus frequency measurement. We have also simulated this using GN oscillator model, which tells that we have a phonon absorption. So from this measurement, we can conclude that MgO is not a good material in order to get a good bandwidth. However, if you want to if you want to get higher amplitude, then MgO is a good. So this is so far we have discussed all the terahertz emission based on persistent Hall effect phenomena. But if you don't have any non-magnetic capping or layer attached with the ferromagnetic layer, still if you incident a laser, a femtosecond laser on the ferromagnetic layer, one would get a terahertz emission. And to understand that, we have to look into this PRL paper, which was published in 1996. So this is a magnetization change in the magnetization when, as a function of time when the laser femtosecond laser incident on the nickel sample, and because of the laser incident, it brings the magnetization and the time scale of this demagnetization and the demagnetization lies in picosecond, which tells that it can be a source of terahertz emitter. But if you attach a very low spin orbit coupling material attached to the ferromagnetic layer, then one would also get a terahertz emission because of this phenomena. However, if you have a ruthenium or gold capping layer, one would get a trap of terahertz current in the ruthenium layer as compared to the gold because of the higher band velocity, since it is not completely d-filled orbital. So to keep this thing in our mind, we also fabricated a sample which is where iron cobalt is used as spin source layer, where we modified the spin dynamic property by doping uranium, high spin orbit coupling material such as rhenium inside the iron cobalt, and we capped with ruthenium. And for as a reference, we also kept the same sample with copper. And we we have measured the magnetic asymmetry using time element specific time resolved magnet optical Doppler effect, and this is a asymmetry which is the change in the reflective intensity, and, and which is proportional to this epsilon xy, which is the off diagonal term of the dielectric tensor, and which is proportional to the saturation magnetics. Then we measured asymmetry at for different elements like iron cobalt at along uh, an edge, and where we found that as we increase the doping, the asymmetry reduces, which is in a similar manner of saturation magnetics. However, we have found a surprising thing here. We found larger asymmetry at around 45 electron volt, which might be corresponding to the ruthenium and edge. So, and then we have calculated the asymmetry using some model, and where we found that at 45 electron volt, there is a enhancement of the asymmetry, which might correspond to the ruthenium. Then we did a asymmetry measurement as a function of time, and what we have found that we found is usual behavior of iron at undoped sample, which can be explained by the demagnetization, the quenching of the magnetization. But what one can see an enhancement in the asymmetry as a function of time, which goes to some certain value after some time. However, this blue dots corresponding to ruthenium plus iron, and when we subtract the iron contribution from this, we got only ruthenium contribution, which is around 4%. And this is a surprising thing for us. And how do we understand that? Since whatever the spin current is generated in the iron cobalt layer, it can also go ruthenium, and because of the high band velocity in ruthenium, it can stay much longer there as compared to the copper. So this behavior we did not observe in copper capped samples, and and this is a calculated change in the magnetization as a function of time, and you can clearly see a similar type of behavior is observed from when we calculate when our collaborator calculated using super diffuse response model. So the similar behavior we observe as a function of rhenium doping, but as we increase the rhenium doping, the peak amplitude of the asymmetry decreases. And how do we understand that? We our theoretical collaborator again calculated the same thing as a function of different reflection coefficient, which we can consider as a different rhenium doping. And as we increase the reflection coefficient, one would get a low uh, change in the magnetization as time. time. So one can say the theory and experiment are more or less in accordance to each other. Then we calculated the generation of spin current in the layer, and for iron cobalt, one would get a usual behavior. However, for different scattering uh, centers or different reflection coefficient, we would get a different type of peak, which is kind of Terahertz peak. And when we do the fast Fourier transform, we get a frequency bandwidth which was around 40 terahertz. As we increase the rhenium doping or the reflection coefficient, we get less bandwidth. So to conclude my talk, we have successfully demonstrated the Terahertz emission from full crystal compound like CFA based Spintronic Terahertz emitter, and one can also tune the Terahertz emission by changing the microscopic properties through strain engraving. And finally, we demonstrated that ruthenium can be a good choice of non-ferromagnetic layer to detect the Terahertz spin current in the Spintronic Terahertz emitter. Finally, I would like to acknowledge my supervisor Peter Shelley and Wolf Paris Charlie, and also my collaborators from different places and also for funding. Thank you so much for your kind attention.
Thank you, Rahul, for the nice talk. And we are already running out of time, but we can take one quick question from Rekha. She can go ahead. Rekha, please.
Yeah, very interesting too. On slide number 10, you have shown the Terahertz emission equation that follows the Ohm's law. And on the
Yes.
left side, you have shown different, on the slide number 10,
Yes.
yeah, this slide. In the left hand side, you have shown different spin source material, different FM material, and
Yeah.
like nickel, iron, cobalt, and their terahertz emission. So I just want to ask why nickel has shown a less terahertz emission compared to other ferromagnetic material. And the
Because
second question is,
yeah, please continue.
And the second question is, can we correlate this terahertz emission to this Ohm's law in the case of nickel?
So to answer your first question, since nickel has a less pure temperature as compared to other ferromagnetic material, so which means when you have a laser incident, it can also create some temperature. So that if that temperature is higher than the Curie temperature, it means your ferromagnetic state is not the ferromagnetic state; it's a paramagnetic state. So that can give a very low terahertz amplitude, and nickel has a very low Curie temperature as compared to other ferromagnetic layers. So this is what I understand from this
Okay.
graph. And if that is the case, then we cannot follow this Ohm's law because that is not in the linear region. We are in the non-linear region.
Mm. Thank you.
Okay, Rahul, thank you for the talk. So,
Andhira, can I
yes.
ask one quick question? Very quick question.
Yes.
Yeah, Rahul, thanks for the talk. I just want to inquire one thing.
Yeah.
You showed that the 40 terahertz bandwidth, right? So which
Yeah.
crystals you are using as a detector for these measurements?
No, actually, that was, I think I did not mention in the presentation. That was not the measurement. It was the calculated from the spin current generation. So
Because we have difficulty to measure such a broad bandwidth using the zinc chloride crystals.
yeah,
So
I can comment on that, but for to begin with, to answer your question, this is not the measurement. This is a calculated fast Fourier transform from this graph, and that is a calculated spin current generation using the super diffusive spin. But to answer your question, second question, like zinc light crystal can detect up to certain terahertz frequency, but it also depends how much pulse width you use for the laser. So if you use, let's say, 10 femtosecond, and if you use 0.1 millimeter zinc lead crystal, one would get, let's say, 30 terahertz approximately,
Exactly.
according to this
Exactly.
Tobias comfort paper.
So I was thinking because this is less than 10, getting 10 laser is very difficult, and then this is the 40 terahertz. So that's why my question. I was wondering
Exactly.
that. Okay, thanks. I would like to discuss with you in detail later. Yeah. Okay. Thanks. Yeah.
Yeah. Okay, Rahul, thank you once again. So we
Thank you.
move on to next speaker. Our next speaker is Diksha Gupta, and the title of her talk is Spin Polarized Hot Electron Induced